Here's more about the cross product thought of as derived from the determinant. Here's a quick summary of what we got so far. We have got two vectors b and c. They span a plane, unless they're collinear, in which case we'll still deal with that quite soon. It's not hard. If they're not collinear, they span a plane and they also form a parallelogram. So there's a unique normal line to that plane. And the two things we know so far about the cross product is that b cross c is perpendicular to both b and c, so it's perpendicular to that plane, and that the magnitude is the area of that parallelogram, which is very handy. That can be very, very useful. So it's a cool way to calculate the area of a parallelogram in three-dimensional space from its coordinates, because we know the coordinate formula for this as well. Here it's focusing on the geometry, but we know the coordinate formula in terms of that kind of the IJK determinant. The big question is, in this picture, for example, is it pointing up or is it pointing down? What's the rule for which one it is? That's the only thing left to verify. That's what I say up here. Okay. So we already have, this is what we're assuming, in my class we've already done this for determinants, we have a right-hand rule for 3x3 determinants. And in particular, it came from a very particular example. The oriented volume, so this is the oriented is where there can be plus or minus. The oriented volume of the box formed by I, j, and k in that order. The convention we had for that is that you have I, j, and then k, that box that those form, that nice cube, that has a volume of plus 1. Okay. That's really the source. That's the convention. It's I, j, k in that order, and you have to draw them in a right-handed way. You have to draw them so that if this is I and this is j, k comes up. Okay. The other way you often see it is I comes toward you, j is this way, and k is this way. That's okay because this is just a rotated version of this guy. If you take this and you rotate it 90 degrees so that this I swings to this I, then you get the same thing. And that's part of a general principle, is that the two conventions, basically, or the two rules we had for figuring out whether an oriented volume of a box should be plus or minus, is that this is plus, and that, I think the only color I have left that's really good is red. It's a little too red, but whatever. It's that if you rotate or morph, deform a box, that doesn't change the sign of the oriented volume. Unless you flatten out the box and produce something with 0, in which case you definitely can go from plus to minus or minus to plus. Okay, but that doesn't count as just a nice little deformation. Okay, so that leads to a right-hand rule for all boxes. It's that if your right hand is the first vector that forms the box, and your fingers go in whatever direction of the second vector that forms the box, and your thumb is going in the third direction, that should be a positive box. Well, that's easy to turn into a right-hand rule for cross products. Because remember, the rule is it's supposed to be that A dot B cross C is supposed to be the oriented volume. This is the first time we've actually had to use that oriented, the sign, plus or minus, the oriented volume of the box. Well, let's test it here. Okay, so let's suppose the box was like this. Suppose this is our A. And we want to see, okay, is this a positive box? Well, yes, it is, because if the hands go in this way and the fingers go in and the thumb goes up, this is going to be a positive box. Okay, so this side in this example is going to be plus. Well, how do I make sure that this side also gives me a positive answer? Well, what's the significance of the sign of a dot product? It's positive when they're generally in the same direction. Okay, so this dotted vector would totally not work. If this were B cross C, then this would dot with A to be negative, but we want it to be positive because this has a positive volume box. Ooh, you can't really see that plus very well. Sorry, that's a plus sign right there, guys. Okay, so that tells us that the B cross C has to be in this direction. So the upshot is that it's got to agree with where your thumb would be for a positive box. So in other words, if I just use the thumb as that third vector, that's going to be the general direction of B cross C. So that's the right-hand rule that many people are familiar with for cross products. If this is B your right hand and your fingers are C, then your thumb is going to be B cross C. Okay, so that's going to be the right-hand rule. Okay, so now that's all the geometric description. This is the traditional full geometric description of the cross product. Here's the direction. Here's the line it goes along. It's perpendicular to the plane. Here's its magnitude, and the right-hand rule is necessary to figure out up or down. Okay, so for my money, that right-hand rule comes from this fact that long ago, when in our class, when we started considering volumes, we found there were really good reasons for considering oriented volumes, and it leads to all these kind of finicky rules about orientations and right-hand rules and things like that. Okay, so that works out this exercise. Okay, and this should be bold. Let's fix that. It's a vector. Okay, so let's look at these guys. We can now take that geometry. Even though we have a calculational formula in terms of the ijk determinant we had way back at the start, near the start of video 1, part 1, we could use that to calculate things like I cross j, k cross j, that kind of stuff. But it's nicer. I think it's nicer to look at it from the geometry now. Okay, I cross j should be a vector that's perpendicular to both I and j, and it should have its length should be the area of the square that's formed by I and j. Well, that's 1. Okay, so it's going to be either plus or minus k. And by the right-hand rule, it's easy to see it's supposed to be k. Okay. Similarly, j cross k, okay, is going to be, let's see, that has to be either plus or minus I, because those are the only two unit vectors, because remember, this forms a unit square, just like this guy, just like the ij square. It's got to be a unit vector that's perpendicular to j and k, so it's got to be plus or minus I. If you work it out, let's draw the picture. So here's, let's use this version. This is one version that's a right-handed thing. You've got to draw them right-handed, or you actually use your real right hand. J cross k, that is, hand goes like this, fingers go up like this, thumb is pointing towards the camera. Okay, and so that's I. And then it turns out k cross I is equal to j. There's a nice little way to remember this that's very, very common when you have three things, but you have to worry about the order. It's called cyclic order. You put them in a circle, and so I goes to j goes to k, and then k is supposed to lead back to I. Then going around in the positive cyclic order gives you plus signs here. Let's think about what happens when you reverse. Okay. What about j cross I? Okay. That is not going to be the same thing. And this is a very, very important thing about cross products. J cross I, going this way, instead of I cross j, well, j cross I, you're going to have, let's see, this is a little bit of a tricky one. You're going to have j here and I coming towards you, and you have to kind of do it yourself. But it turns out the thumb goes down this way. Minus k. Huh. So when you switch the order of two things in a cross product, at least in this example, it seems to give a minus sign. Well, you can convince yourself that k cross j is minus I, and I cross k is minus j. So that's when you go against cyclic order, you get the minus signs. Well, I claim that's a very general purpose, a very, very general thing. And that's what this next exercise is about. Or that's part of what the next exercise is about. Okay, so that last equation is that if you switch the order in a cross product, I claim you just get the negative. Okay, two ways to see that. One is, remember, B cross A, it's still supposed to be perpendicular to A and B, so it's along the same line. Let's have A and B here. Okay, it's supposed to be either here or here. Okay, it's supposed to have the same magnitude. The magnitude formula was the area. That had nothing to do with the order. Okay, so these are unchanged. The only thing that could change is the right-hand rule. And where did the right-hand rule come from? It came from the oriented volume stuff. Okay, so remember that when you switch two of the vector of these row vectors, in a determinant, switching any two rows in a determinant, that changes the sign. Okay. That leads directly to the fact that the right-hand rule is very sensitive to the order you put the vectors in. And so, in fact, when you switch two rows in a cross product, that's the reason why the right-hand rule is telling you that you're going to change the sign. So the only thing that could happen is a change in sign, and it always happens because of the fact that it's really about switching rows in a determinant. Okay? So this is one of the things that we focused on in our class, one of the fundamental properties of the determinant. In fact, everybody should focus on it. It's so fundamental that when you switch the vectors, the sign changes. That leads directly to this property of the cross product. Okay. What about these two rules? With the first two rules here, I can't select them separately. But like this one, God, I'm trying to select them separately. Okay. Whoa, you don't need to see that. Okay. Well, those also come from the determinant as well. Here's a couple of facts that we learned in our class about the determinant. They're called multilinearity. That when I take the determinant of, say, A and, like, let's put in U plus V, let's see, something like that. That's equal to the corresponding thing. So remember, it's really important. I'm not just adding two matrices. I'm keeping two of the rows absolutely the same and just adding two vectors in one of the rows to make a sum in that row. Okay, that's part of the multilinearity package. It's a wonderfully important property of the determinant. Let's phrase that in terms of the cross products. It says that A dot U plus V cross C equals A dot U cross C plus A dot V cross C. And remember, this is supposed to happen no matter what the vector A is. Only way that's going to happen is if this vector is the sum of these two guys. Okay, you'd have to go into a little bit of work to really prove that, but it's pretty plausible that would be unbelievably weird if no matter what vector A you dotted it with, you always got these same dot products, unless this vector was equal to the sum of these guys. And that is true. So again, if you want a super standard of rigor, I don't think that's passing muster, but that's it. You can make it into a very nice proof of this fact. So it says that the cross product distributes over addition. Okay. And similarly, let's just change this in place. Let's just take this and change it into like a k times u. This was another thing that we knew about determinants. And the main point I'm making here is once you know all these facts about determinants, you do not have to reprove them. I'll just erase this. For the cross product, okay? It says that A dot KU cross C equals K times A dot U cross C. Okay, and again, this is true no matter what the vector A is that you're dotting in. Only way that's going to happen is if this vector, just to erase the A's, is equal to this guy. So you can factor out a K. You can get this in various ways. You can get it from the geometry. You can get it from the explicit formula. But I wanted to point out that they're actually essentially exactly the same rules. These rules are exactly the fact that the determinant is multilinear, that you can take sums or constants out of any row, and that it has the flip property of minus. It's called the alternating property of the determinant. Okay. And I make a comment here in the text version that it's really crucial for the terminology we use that the distributive law holds. Okay. Only if you've got a way to add two gadgets, like we know how to add vectors, the only way you should ever call some other operation a product is if it satisfies a distributive law. And so that's what really allows us to start thinking of this weird operation as a product. It doesn't look like just multiplying two numbers. It has to do, the formula has to do with multiplication, but it's got various other properties. It's anti-commutative. That's this funky property here of switching signs. And it's defined in terms of areas and geometry and volumes and right-hand rules and stuff like that. In what sense is it a product? In what sense is it a way to multiply vectors? Well, this is the answer. Because it satisfies this rule, that makes it deserve the name product. Okay. And then I'm just going to let you look at these, and you can pause the video if you want, and think about these two exercises. The hint here is that if you switch the order, most of the time, a lot of these are the same, but you can get the minus sign. It's a little tricky to really convince yourself of which ones deserve the minus sign. But keep thinking right-hand rule, or keep thinking that the cross product is anti-commutative, the dot product is commutative. That'll give you the answer. And then the associative law is a good one to try. By just trying ij's and k's, you can convince yourself that unfortunately the associative law is not true. Turns out that that has some very, very deep consequences, which I'll probably not be able to go into.